We will now start to discuss plastic deformation, and we will do that in the same way in the beginning as we did with elastic deformation. That is, we want to look at the deformation of an aluminium band. As we did before, we did put on a little load, and then we took away the load, and the deformation went back. But if we increase that load, what's going to happen? We will do that now. We increase the load a little bit more, and then we take away the load, and what do we see? Well, we see that we have obtained a plastic deformation that remains. We have passed an interesting point, the transition point between elastic and plastic deformation. That point is called the yield stress, or actually that is the strength of the material. Now we're going to look at this in a diagram also. We will look at the same diagram as before, the stress-strain diagram. And we see here we have the stress on this axis and the strain on this axis. And we start putting on a load. And there is a straight line as long as this is elastic deformation. But at a certain point we come into the plastic deformation. And here the line turns over into a more smooth curve like this. So this is a plastic deformation part. And this point, which is the yield strength of the material, can be marked here. We call it, in this case, sigma S. Then we look at the curve, we come to this point, and we deload the material, we take off the load. Means that we go down here, parallel to the elastic deformation line. And then we see here that we come down here, not to zero this time, we come down to a certain deformation, a certain strain. And this is the remaining plastic deformation in the material. Now, if we put on the load again, we will follow this line up and then continue like this. If you further continues, we sooner or later will come to a situation where the material breaks. And that point we call the tensile strength. We can mark that point also. And normally it's called sigma M. These denotations can be very different. You can also use R for this, RM and RS. You can also use R0.2 for this one. That are denominations you can find in the literature for these properties. When we discussed the elastic properties, we saw that for different alloys of aluminium, also both for pure aluminium and for alloyed and hardened aluminium, they had more or less the same Young's modulus, the same stiffness. But when we should start discussing the yield strength and tensile strength, we will see that it's completely different. Actually, for aluminium alloys, you can have a span of a factor of 10 between the yield strength for pure aluminium and the yield strength from aluminium alloy with very high alloy content and hardened. The same goes also for steel. We shall now look into an example and compare two aluminium alloys and see what happens. Now we will look at the plastic deformation of two aluminium bands. One pure aluminium band and one alloyed and hardened aluminium band. We shall now start to put on the load on these two. And the weights are of course the same for the two bands, and it's about 1.3 kilo. It's one steel and one aluminium load. Here it is also important, of course, that we have the same length that are coming out of the desk. So we adjust the length and then we move out, increases the length more and more, and we see here that the pure aluminum band starts to deform more and more if you compare it to the alloyed band. Now we can take the bands and deload them and see what has happened with the deformation of the bands. If we look at the alloyed band, we see that it's straight, it has not deformed plastically, it has only deformed elastically. Looks as before, while the pure aluminum band has deformed plastically rather strongly. Let's discuss the results based on the diagram we looked at before. If you assume that this curve, which we drew before, corresponds to the pure aluminum alloy, which we loaded past this yield strength point up to a point here, and then we deloaded and got some deformation. If we start talking about the other alloy, the one which did not deform plastically at all, we can continue to draw this line. Assume now that we are looking at the other alloy, the alloy which was hardened and alloyed. Then the elastic line continues. Now we don't know how far, as we need not go so far to get plastic deformation. But anyway, we went to this position, and here we had no plastic deformation. Assume that at this point somewhere we start to get plastic deformation in that case. Then the yield strength for that one will be here. Then maybe we can find another alloy which is even harder, and that will continue like this, and then bend off up here with the yield strength there. So the yield strength points can vary for different aluminum alloys, but they will all be on the same elastic line. As long as the deformation only is elastic, we will follow the same line, but when we reach the yield strength point, the curve will bend off. What control the yield strength? Forces between the atoms are important, but they cannot explain the variations between different alloys of the same base material. You will also see that they cannot explain the level of the strength either. Based on the forces between atoms, it is possible to calculate the theoretical strength of a material. If you assume that all atomic bonds in the plane transverse to the deformation direction is broken at once, we can obtain an approximate value. This has been done. That approximate value is roughly elastic modulus divided by 15. That is like this. Theoretical is roughly elastic modulus divided by 15. If we now calculate the theoretical value for a real material, for instance for steel, we know that the elastic modulus for steel is about 220 gigapascal. That means that the theoretical strength will be about, that is 220 gigapascal divided by 15. That means a value of about 15,000 megapascal. The theoretical strength of steel. But what is the real strength of steel? Well, if you look in the tables, you will find strengths of steel in the range from about 300, maybe even 200, up to 2000 megapascal. And we see that this is much, much lower than the theoretical value. Actually, it's about 50 to 10 times lower than the theoretical value. And that have to be explained.